everyone, this is Kalpana here. In this video, we are going to solve a differential equation from higher order linear differential equation. So let's get going. Problem. Solve d square minus 2d plus 2 into y equals to e power x square plus 5 plus e power minus 2x. So firstly, let's find the order and degree of the given differential equation. Identify the highest derivative here. D square is the highest derivative, so order will be 2. And highest power of the highest derivative is a degree. Degree is 1. Or just write the given differential equation as d square y minus 2dy plus 2y equals to e power x square plus 5 plus e power minus 2x. We know that d is a differential operator. Then d square will be d square by dx square. Now we can write our equation as d square y by dx square minus 2 into dy by dx plus 2y equals to e power x into x square plus 5 plus e power minus 2x. Here d square y by dx square is the highest derivative, so order will be 2, and highest power of the highest derivative is a degree. Degree is 1. Now coming to the problem. Given differential equation, d square minus 2d plus 2 into y equals to e power x into x square plus 5 plus e power minus 2x, which is an operator form. F of d into y equals to q, where f of d equals to d square minus 2d plus 2 and q equals to e power x into x square plus 5 plus e power minus 2x. Now we need to find the general solution to the given equation, which is given by y equals to yc plus yp. We know that yc is a complementary function, yp is a particular integral. We'll find yc using the roots of the auxiliary equation of the homogeneous equation of the given non-homogeneous equation. Simply by putting RHS to 0, we'll get the homogeneous equation. And we'll find yp using 1 by f of d into q. Right? So firstly, we'll find yc using the auxiliary equation of the homogeneous equation. We know that the auxiliary equation of f of d into y equals to 0 is f of m equals to 0, where f of m equals to, we have f of d square minus 2d plus 2. Let's replace differential operator with m so that we'll get f of m equals to m square minus 2m plus 2. Then our auxiliary equation becomes m square minus 2m plus 2 equals to 0. Now we need to find the roots of this equation. We'll find roots of this equation using the quadratic equation. M equals to minus b plus or minus square root of b square minus 4ac by 2a. Just compare this equation with quadratic equation in m. am square plus bm plus c equals to 0. So that we'll get a equals to quotient of m square 1 and b equals to quotient of m. Equate the quotient of m, we'll get b equals to minus 2 and c equals to 2. Right? Now let's find the roots. M equals to minus b, minus of minus 2 plus or minus square root of b square minus 4 into a, for a equals to 1, into c, c is 2, by 2 into a, 2 into 1. This is equals to 2 plus or minus square root of minus 2 whole square is 4 minus 4 2s are 8 by 2, which is equals to 2 plus or minus square root of minus 4. Minus 8 plus 4 is minus 4 by 2. This is equals to 2 plus or minus. We can split minus 4 as minus 1 into 4 by 2 is equals to 2 plus or minus. Now split square root of minus 1 and into 4 as square root of minus 1 into square root of 4 by 2. Since we know that square root of minus 1 is I and square root of 4 is 2. So we can replace square root of minus 1 with I and square root of 4 with 2. Then we'll get 2 plus or minus I into 2 by 2. Right? Now take 2 common from the numerator. We'll get 2 times 1 plus or minus I by 2. 2 gets cancelled and we'll get 1 plus or minus I, which is a pair of complex conjugate. Right? Therefore, m equals to 1 plus or minus I are the roots of our auxiliary equation f of m equals to 0, which is a pair of complex conjugate. Right? Fine. We know that a plus ib is a complex number and its conjugate is a minus ib. If a minus ib is a complex number, its conjugate is a plus ib. Then we can call a plus or minus ib as a pair of complex conjugate. If we have complex conjugate roots, then yc will be c1 e power ax into one constant cos bx plus another constant sin bx. Right? In our case, we are having n plus or minus I for a equals to 1 and b equals to 1. Our complementary function looks like yc equals to e power 1 into x into c1 cos, for b equals to 1 we'll get 1 into x plus c2 sin 1 into x. Right? Then yc equals to e power x into c1 cos x plus c2 sin x. So we got yc. Now let's find yp. Particular integral. We'll find particular integral using 1 by f of t into q. We have f of t and q where f of t is d square minus 2d plus 2 and q is e power x square plus 5 plus e power minus 2x. We can write it as 1 by f of d into first term plus 1 by f of d into second term plus 1 by f of d into third term. Right? Now we can find each term separately. First let's find the first term. 1 by f of d into e power x square. Right? This is of 1 by f of d into e power ax into v form. Right? So here we are going to shift e power ax towards left by replacing d with d plus a into v. Later we'll operate v with 1 by f of d plus a. So now compare e power x with e power ax, and for a equals to 1 we'll find d plus a, which is equals to d plus 1. Shift e power x towards left by replacing d with d plus 1. We'll get d plus 1 whole square minus 2 into d plus 1 plus 2 into x square is equals to x square into 1 by expand d plus 1 whole square using a plus b whole square. We'll get d square plus 1 plus 2d minus 2 into d is minus 2d minus into plus minus 2 into 1 2 plus 2 into x square. Here minus 2 plus 2 gets cancelled and plus 2d minus 2d gets cancelled. So we'll get e power x into 1 by d square plus 1 into x square. See, in the denominator we are having d square plus x, right? In decreasing order. So let's write it in ascending order. Then we'll get e power x into 1 by 1 plus d square into x square. See, this fraction is of 1 by some 1 plus x form, so we can write it as 1 plus x whole inverse, because this is of some 1 by function of d, some function of d into x power k form, right? Here we are having for k equals to 2, x square, right? For k equals to 2, we'll get only derivative of x square and d square of x square. Okay, we'll get derivatives of x square till d square. And from d cube, we'll get derivatives of x square 0. That means higher derivatives of x square become 0 for k equals to 3, 4 and so on. So let's see. This is equals to e power x into, now we can write 1 by 1 plus d square as 1 plus d square whole inverse into x. Okay, whole inverse into x square. Now we'll expand 1 plus d square whole inverse using the formula 1 plus x whole inverse, which is equals to 1 minus x plus x square minus x cube plus so on. So before expanding 1 plus d square whole inverse, we'll find the derivatives of x square. Derivative of x square is 2x, d square of x square is derivative of x square. We have the value for derivative of x square, which is 2x. So now we can write this as 2 into derivative of x. We know that derivative of x with respect to x is 1. This is equals to 2, right? Now let's find d cube of x square is equals to derivative of d square of x square. Since we are having d square of x square value, which is 2, a constant, and we know that derivative of a constant with respect to x is 0. So we'll get d cube of x square is 0. Likewise, we'll get d power 4 of x square is equals to 0 and so on. In general, we can write that as d power k of x square equals to 0 for k equals to 3, 4 and so on, right? In general, d power k of x square equals to 0 for k equals to 3, 4 and so on. So now, keeping all these derivatives in mind, we'll expand 1 plus d square whole inverse. Okay, we can neglect the higher derivatives from d cube, d power 4 from here. Right? Fine. This equals to 1 minus, for x equals to d square, we'll get d square plus d square whole square minus d square whole cube plus so on, which is equals to 1 minus d square plus, we know that a power m whole power n equals to a power m into n. So we'll use this formula here. D power 2 whole square is 2 2s are 4. D square whole cube is 2 3s are 6 plus so on. So here we are getting higher derivatives from the third term, right? So from here we are going to neglect all the terms from the third term. Okay, so we'll write only, or we'll use only the first two terms. Now coming to the problem, this is equals to e power x into, now expand 1 plus d square whole inverse, which is 1 minus d square plus d square whole square minus d square whole cube plus so on into x square. Which is equals to e power x into 1 minus d square plus d power 4 minus d power 6 plus so on into x square. Since we know that higher derivatives from d power cube, d cube is 0. So we'll neglect all the higher derivatives from d cube, right? Since d power k of x square equals to 0 for k equals to 3, 4 and so on. So neglect higher derivatives or higher derivative terms from d cube, d power 4 and so on. Okay. So we are going to neglect all the terms from here. Then we'll get e power x into 1 minus d square into x square. This becomes e power x into 1 into x square is x square minus d square of x square, which is equals to e power x into x square minus j square of x square value is 2. Therefore, 1 by f of d into e power x square is equals to e power x square into x square minus 2. We got the result from the first term. Now let's find the result of the second term. Second one, 1 by d square minus 2d plus 2 into 5. So here we are having constant, right? So we can write this constant as 5 into some e power 0x. Since we know that e power 0x is e power 0, which is equals to 1, right? If we can write 5 as 5 into 1, 5 into 1 is obviously 5. So we can write 5 as 5 into 1. Then we can replace this 1 with e power 0, right? And also e power 0 can be written as e power 0x. Okay. We have constant. We'll write that constant as 5 into e power 0x simply. Now this becomes 1 by f of d into 5 into e power 0x. So this is of 1 by f of d into e power ax form, right? Take this constant towards left. We'll get 5 into 1 by f of d into e power 0x. Now this is of 1 by f of d into e power 0x form. Sorry, e power ax form. Now for a equals to 0, for a equals to 0, just compare e power 0x with e power ax, and for a equals to 0, we'll find f of 0. Since f of d is d square minus 2d plus 2, let's find f of a, which is equals to f of 0. Replace this d with 0, then we'll get 0 square, 0 minus 2 into 0 plus 2, which is equals to 0 minus 0 plus 2, which is 2, non-zero, right? Since f of 0 is non-zero, so we can replace d with 0. Then we'll get f of 1 by 0 whole square minus 2 into 0 plus 2 into e power 0x. What happens if we get f of 0 is 0? We'll get 1 by 0 into e power 0x. Since 1 by 0 is undefined, so total term becomes undefined. So always remember that the denominator must be non-zero. Right? Then this becomes 5 into 1 by 0 minus 0 plus 2 into e power 0x, which is equals to 5 into 1 by 2 e power 0x. We know that e power 0x is 1. So let's replace e power 0x with 1. Then we'll get 1 by 5 into 1 by 2 into 1, which is 5 by 2, right? 5 into 1 by 2 is 5 by 2. Therefore, 1 by f of d into 5 is 5 by 2. Now coming to the third one or third term, Third term is of 1 by f of d into e power ax form. 1 by f of d into e power ax form. Compare e power minus 2x with e power ax and we'll get a equals to minus 2. Here we are having f of d equals to d square minus 2d plus 2. Let's find f of a, which is equals to f of minus 2. Replace d with minus 2, then we'll get minus 2 whole square. Minus 2 into minus 2 plus 2, which is equals to minus 2 whole square is 4. Minus into minus plus 2 2s are 4 plus 2, which is equals to 4 plus 4 8, 8 plus 2 10, non-zero. Since f of minus 2 is non-zero, so we can replace d with minus 2. Then we'll get minus 2 whole square minus 2 into minus 2 plus 2 into e power minus 2x. Is equals to 1 by minus 2 whole square is 4. Minus into minus plus 2 2s are 4 plus 2 into e power minus 2x is equals to 1 by 10 into e power minus 2x. Or we can write it as e power minus 2x by 10. Therefore, 1 by f of d into e power minus 2x is e power minus 2x by 10. So now, coming to yp, we have the result obtained from first term, second term and third term, right? So let's place all the results obtained in yp. Yp becomes, result obtained from the first term is e power x into x square minus 2 plus result obtained from the second term 5 by 2 plus result obtained from the last term e power minus 2x by 10. So we got the required yp. Now we are having yc and yp, right? So let's write the general solution. The general solution is given by y equals to yc plus yp. Then y equals to yc, we are having e power x into c1 cos x plus c2 sin x, and yp is e power x into x square minus 2 plus 5 by 2 plus e power minus 2x by 10. This completes the problem. So we have seen a problem from higher order linear differential equations in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.